Hello, everybody in Taiwan. I'm very happy to show these materials today, and thank you very much for inviting me this meeting seminar series. And today I'd like to talk about solar wind interaction from the viewpoint of spacecraft observations around the moon by mainly Kaguya orbiter and partly Artemis spacecraft. First of all, the moon is almost every day exposed to space plasma. That is the sorry, laser pointer. Oh. Do you see my pointer? Yeah.
Yes, yeah.
Okay, thank you. The moon is stays only 4 days in the Earth magnetosphere, and for other 25 or 26 days, the moon is exposed to the solar wind, incident solar wind plasma, as shown here, and the behind of the moon along the solar wind flow, very tenuous region is formed. This is called Lunar Wake. And actually, there are a lot of topics of the solar wind interaction with the moon environment. And today, I would like to talk about these red-colored topics. So one of them is plasma interaction with solar wind, and wake formation, and magnetic anomaly interaction, and resultant wave excitation around the magnetic anomalies. So it's a kind of 月面电子环境学 in Chinese, and 月面電磁環境学 in Japanese. So my viewpoint is it's one of the solar wind interactions with planets or moons. If the planets are very large and have large and strong magnetosphere, the interaction is in the scale of MHD scale, and a clear bow shock is formed, and the magnetotail is formed. But in case of the moon, because it does not possess a global magnetosphere or thick atmosphere, there are no magnetosphere or no ionosphere. But the lunar surface is partially and strongly magnetized, as I will show you later. So interaction is takes place in the much smaller scale, but very interesting. It's a kind of kinetic scale physics. First of all, the crystal fields plays a very important role in such solar wind interaction, and but at the non-magnetized lunar surface, the space plasma can directly interact with the lunar surface, lunar regolith. And from the viewpoint of very large-scale interaction, there formed a lunar wake in the solar wind region behind the solar wind flow, along the solar wind flow behind the moon. Anyway, the typical physical scale in the lunar solar wind interaction is typically ion gyro radius, ion gyro scale. So one question we have is, how does a solar wind directly interact with such a small scale object, such as the moon? I should like to skip this one, but this is the same thing I I mentioned before. So first of all, the lunar surface is charged. The day-side surface is basically positively charged because under the sunlight UV radiation, photoelectrons are emitted from the day-side surface. So relatively speaking, the lunar day-side surface is positively charged. On the other hand, lunar night side is negatively charged because the solar wind electrons can directly access much more easily than solar wind ions. So, and the spatial scale, this is very important because the order of solar wind proton gyro radius is about 100 kilometers under the condition of typical solar wind parameters around the moon. And please note the lunar radius is about 1,700 kilometers, and this is much larger than the proton gyro radius. But as I mentioned before, there are partially very strongly magnetized regions on the lunar surface. And what is important here is the spatial scale of such crustal magnetic field. This is the lunar crustal magnetic field model composed by Kaguya magnetometer data. The value is normalized at the 30 kilometers altitude from the lunar surface. And as you see here, this is left side is corresponds to near side of the moon, and the right side corresponds to the far side of the moon. As you see here, very large and strongly magnetized region exists on the lunar far side and in the southern hemisphere. Actually, this is around the South Pole Aitken Basin. Yeah, around here. And the bottom line here is its spatial scale is about from 100 to 1,000 kilometers. Now, actually, it is comparable to solar wind proton gyro radius. So there must be some interaction with lunar crustal magnetic fields and the incident solar wind protons. So actually, before Kaguya or lunar prospector measurement, this kind of interaction has been known. This magnetized region is quite compressed by the solar wind dynamic pressure. This is a very classical view of the solar wind interaction with the lunar crustal magnetic fields. And anyway, at that time, the very strong solar wind dynamic pressure seems to play a very important role in such an interaction. And actually, this was a measurement at the lunar surface, magnetometer at the lunar surface. And after that, by using lunar prospector data, which was obtained in orbit around the moon, such very interesting magnetic field enhancement was detected. And this reminds us, makes us to imagine that there took place some kind of bow shock-like behavior around the lunar magnetic anomalies. And actually, time flies like an arrow, but we have a lot of Kaguya spacecraft data. We obtained 1.5 hour operations data, and actually it was a polar orbit, as you know, and typical height from the lunar surface was about 100 kilometers. But in the latter half of the operations, we make it lower and lower, and actually 20 kilometers altitude observation was realized, and the polar orbit period was about 2 hours, and we measured ions, including composition, as Yokota-san talked about it this morning, and electrons and magnetic fields and electric field wave components. So actually, there are 4 independent sensors for the detection of plasmas, and 2 of them are installed on the backward of the Kaguya spacecraft. One is IEA, this is for solar wind ion measurement, and the ESA2 for electron measurement. And another couple of sensors faced upon the lunar surface, directly upon the lunar surface. And one of them, IMA, is for detection of ions from the lunar surface. And ESA1 is for the detection of electrons. So let us see the plasma direct interaction with lunar magnetic anomalies. Actually, this is 100 kilometers altitude data for 1 revolution around the moon. And let us, the non-hatched region corresponds to the day side region. And this is North Pole, and the Kaguya flied on the day side and went to South Pole. And from the top, electric field, frequency, and the magnetic field, and the connection to the lunar surface, and electron energy time spectrograms from 2 electron sensors. And these 2 panels are pitch angle distribution of electrons. And the solar wind ions, these are protons and alpha particles. And the final one is ion energy time spectrograms, including the heavier ions detected around here. These low energy components are heavy ions from the moon. Actually, these components include sodium or potassium or something like that, as mentioned by Yokota-san this morning. And you see some component, reflected component, and you also see some weaker flux around here. And actually, these strong flux reflected from the lunar surface shows the magnetic anomaly interaction with the solar wind. These flux are reflected right above the strong magnetic anomalies. And on the other hand, these lower flux is component directly came back from the lunar surface at the non-magnetized lunar surface. And these are actually a new finding of Kaguya measurement. So what do we see at the lower altitude above the crustal magnetic field? Actually, this was 100 kilometers altitude, and we almost do not see almost no modulation of incident ions, but just electron heating was observed. So if we go down to very low altitude at 20 kilometers from the moon, there are electron acceleration right above the strong magnetic anomaly. We see, first of all, we see very spiky enhancement of magnetic field at the spacecraft orbit, and the deceleration of solar wind ions and acceleration of solar wind electrons are simultaneously detected. And of course, very high fluxes of reflected protons right above the strong magnetic anomalies were detected. So anyway, incident solar wind ions are decelerated, and on the other hand, solar wind electrons are downward accelerated. It means there should be formed upward electric field. So this is a punch picture of what is going on right above the such strong magnetic anomalies. Because of the difference of masses of protons and electrons, solar wind protons can more deeply come into the magnetized region than electrons. So due to the charge separation, upward electric field is generated as displayed here. So this electric field decelerates ions, incident ions around here, but simultaneously, incident solar wind electrons are accelerated by the electric field. So this is a kind of whole MHD effect. This is almost the same thing of the gradient B is formed around here, and this is rotation B shows the electric current. So what is going on is almost almost similar to Earth magnetopause current layer. It's very similar to what is going on around the lunar magnetic anomaly. Actually, I will skip this one because this afternoon Martin Huizer will talk about this one. But anyway, this is a very interesting result about the lunar strong crustal magnetic field. So let me shortly summarize the direct interaction of solar wind protons at the lunar surface. Above the non-magnetized surface, about 1 to 3% of incident solar wind protons are scattered as protons. And actually, some of them are scattered as a negative hydrogen ion, but unfortunately, we didn't have such negative ion detector. So we have never seen such an negative ion component. And about 20% of incident solar wind protons are neutralized at the lunar surface. And above strong crustal fields, above up to 50% of incident solar wind protons are reflected by magnetically or upward electric field. and some of them might be deflected, and this deflection is consistent with the result of neutralized energetic atoms. So please stay tuned to the Martin's talk. And by the electric field wave detector, we detected some broadband electrostatic noises as shown here. This is a kind of frequency time spectrogram for 6 hours. This is for 6 hours, and this is for 6 hours. So there are totally there are 6 revolutions around the moon. And as you see here, there are strong wavy activities, and these broadband electrostatic noises corresponds to electrostatic solitary wave structure. And actually, they were detected above the South Pole Aitken Basin. Physically speaking, these electrostatic solitary wave structure is a kind of due to a kind of electron two-stream instability. So one idea is incident electrons and backscattered electrons above the strong cluster magnetic field makes the such kind of two-stream instability. It's a kind of beam instability. And non-magnetized regions, it is expected that the lunar surface is facing the space weathering effect. And space weathering is a kind of change of surface color of planets or moons or asteroids. No, it's a asteroid. This is wrong. Asteroids and airless are commonly seen for the surface of airless bodies. And the possible cause is micrometeorite impact, bombardment, and cosmic rays, and solar wind implantation. And recently, one of my colleagues, Nakauchi-san at ISAS, published a paper in Icarus, and he did some nice experiment on the ground, on the Earth. I mean, in the laboratory to show the solar wind implantation actually makes some water molecule, and it plays a very important role in space weathering as well. Actually, this is simulation results, so I skip this one today. So about the lunar day-side surface. Actually, I talked about the solar wind interaction on the lunar day-side so far, and an interaction between lunar surface or planetary surface and the space plasma surrounding that is to know electromagnetic phenomena at much lower altitude or near the surface. I guess the lowest altitude of Kaguya spacecraft above the strong cluster magnetic field was 20 kilometers. But actually, something take place below the orbit. I mean, about the I guess it's about 5 kilometers altitude or 10 kilometers altitude or something like that. Anyway, low altitude measurement is necessary to understand what is going on at the cluster magnetic field. And if I have enough time, I would like to talk briefly about lunar wake observation. Actually, a traditional view is presented on the left side, and because the solar wind protons solar wind proton speed is much faster. Bulk speed is much faster than its thermal speed. Solar wind protons are only gradually come into the night side, and electrons can easily access the night side region because its speed is very high. So there should generate the electric field around the wake boundary, and shown here. And by this electric field, solar wind protons gradually come into the night side region, as shown here. But anyway, this is a classical or old view. So new view will be presented here. So actually, these data shows 3 revolutions around the moon, and this is day side, night side, day side, night side, day side, night side. And these black, the top panel shows the ion energy time spectrogram, and as you don't see anything here, this is the typical wake region. We don't see typically we don't see ions in the wake, and same here. But we clearly see solar and proton entry here. These are ion signal, and these ions These ions are from the These ions are once scattered on the lunar surface, and according to the depending on the IMF strength and IMF direction, it has a very large gyro radius and can directly access the lunar night side region, as illustrated here. And actually, these protons accelerates electrons as well along the IMF to maintain the charge neutrality in that wake region. And these incident electrons are kind of two stream, like bi-directional beams along the magnetic field. So it's kind of that kind of two-stream electron beams gives rise to the generation of electrostatic noise, as shown here. Anyway, it is a kind of electrostatic solitary wave. So it's actually lunar deepest wake is very noisy region, you know. So this is the evidence of electron bidirectional electrons, and this is the pitch angle distribution of electrons. And as you see here, in the parallel direction and the anti-parallel direction, the electron energy flux enhancement were observed. So actually, this is bidirectional electrons. So current understanding is as summarized here. So in such a configuration, day-side scattered protons, solar wind protons, can directly access the lunar night side region, and which we called proton-governed region. And proton-governed means the proton comes first, and that attracts ambient electrons, as shown here. and these electrons are very important, plays very important role in wave excitation as presented here. And this is recent observations by Artemis spacecraft. They detected electron holes in the distant Lunar Wake, as shown here. So, our Kaguya measurement was only 100 kilometers around the moon, also almost attached to the lunar surface. But thanks to the very large orbit, Artemis spacecraft can detect the such electron holes in the wide region around the lunar environment. So actually, Lunar Wake is elongated as shown here, and some electron hole structure were detected as shown here. So getting far from the moon, and actually this is Harada-san's Jasper Hareka's review article. Actually, there are a lot of wave generation mechanism around the moon, and this is a statistical study, statistical maps of electron anisotropy or wave activities around here. So anyway, there are a lot of wave activities around the moon and in space around the moon. So it's not very quiet space, but it must be very noisy and active in terms of plasma waves. So these waves are generated by such a very interesting shape velocity distribution function. And some of them are beams. These are solar wind beams and reflected beams, and this are kind of beam interaction. And these are electrons. Electrons lost cone generates the some narrowband Whistler waves, and also beam component generates the broadband electrostatic emissions, as shown here. This is also mentioned by Harada-san and Jasper Hareka's review paper. So I will stop my talk here anyway. So I will briefly talk about the direct interaction of the lunar surface and incident solar wind, including magnetic anomaly interaction and wave excitation and wake formation. And actually, there are a lot of interesting topics, including H2O molecule generation on the lunar surface by the solar wind hydrogen implantation. And actually, we are going to study lunar relation between lunar topography and electromagnetic environment. So we are actually, this is our next plan. So okay. Anyway, I will stop here today. So thank you very much.